at least. I'd like to introduce our speaker. It's a pleasure and delight to have Ann Sheehan here. She is, I'll go through her education. She got her degree in, bachelor's degree in geophysics from University of Kansas, and she got her PhD in geophysics from MIT. And she is a professor at the Department of Geological Sciences at CU. She's also a fellow in the Cooperative Institute for Research in Environmental Sciences series, where UNAVCO started. And she's also Associate Director for Solid Earth Sciences at Ceres. She is currently an EarthScope speaker. She has been an IRIS SSA Distinguished Lecturer. She's won a Sloan Foundation Mentoring Award and the Distinguished Alumni Award from the University of Kansas. Go Jayhawks. And today the title of her talk is The Roots of the Rockies, Deep Crustal Imaging Using USArray. Ann? That's true, yeah. I might be too late. Okay, well, thanks for inviting me. I'm glad to be here. I'm actually going to talk a lot more about seismology than geodesy. I don't know if I have any geodesy in here, so I think that's it. Yeah, you guys will manage. And so I'm going to be talking about some work I've done in the Rocky Mountains over the years, about a flexible array EarthScope experiment we did in Wyoming, also a little bit about some of the tectonics of the Rocky Mountains. And let's see. Oh, okay. All right. So I have a lot of collaborators that I would like to acknowledge. Uh-oh.
Okay, enter spacebar.
Space, Or just tap this? Oh, yeah, interesting. I don't know why. Okay. So yeah, a lot of collaborators. I think as I show people's work, I'll just try to acknowledge them. And this is mostly for the Bighorn Project. It was a big multi-institution project, collaborative with Texas A&M, Wyoming, Colorado College, University of Texas at El Paso. And so I'm going to start out talking about the tectonic history of the Rocky Mountains, some of the different models that are out there to explain the Laramide orogeny, and then go into some of the contributions from seismology, some of the earlier studies from CoCorp, what people could do with the Global Seismic Network, and then what the IRIS Pascal facility was able to help enable, and then get into what has been done a little bit with the USArray TA, transportable array, and the flexible array, and then wrap it up. So the Laramide orogeny was a major tectonic event that happened 40 to 80 million years ago, and it was what formed the current Rocky Mountains. It's quite unusual to have a big mountain range so far away from the plate boundary, and it's been a big mystery to a lot of folks over the years. I'm going to show a few slides. These are from Ron Blakey, who is in Northern Arizona University and has made a number of paleogeography images that kind of show the geologic history based in large part on sedimentary and igneous rocks through time, and also plate reconstruction. So this is showing a picture of what was going on 150 million years ago. So the Atlantic Ocean is opening. So you've got east-west extension going on. Off the west coast of North America, there's a series of island arcs and subduction going on. And this also has kind of the current plate boundary, or current state on here, though things have moved quite a bit. But that's kind of for reference. So this is marching up in time, 115 million years ago in the early Cretaceous. So subduction is still ongoing. And then in the late Cretaceous, there's a western interior seaway. So this material was all at sea level, and one can go through the sedimentary rocks from around here and see things like the Lion sandstone going into sands, then shales, then limestones from deep water as you get out into Kansas. And there are a lot of fossil fish and so forth out in Kansas from that time. In the late Cretaceous, this is a picture. So the Kula Ridge is intersecting. The plate geometry is changing somewhat out here. Okay, just marching up in time. The Paleogene. And so the Farallon plate, kind of the remnants of it are here. So we think it was still subducting. And to reconstruct this plate history, we can use the geology and also can use a lot of information from magnetics from the ocean. So there's a lot of plate tectonics that was done before GPS came around. And so it's pretty important for getting the long time history. And it is pretty amazing, as you all know, that the current day GPS and the long record from the global plate motions are in pretty good agreement. So this is showing some of the magnetics offshore the west coast. This is just a cartoon from Bunge and Grand, a paper that came out in 2000 showing kind of some of their interpretation of what was going on with the Farallon plate subducting under North America. And it was thought that this subduction of this plate had a lot to do with where the Rocky Mountains have ended up. This is from Tanya Otwater at UC Santa Barbara. So this is an animation just showing the tectonics. Time is up here, 60 million years ago. And looks like this stopped. But this is probably something that many of you have seen many times. But it's good to kind of get an idea. So here's the remains of the Farallon plate, which is now the Juan de Fuca plate. The rest of this plate is gone. It's underneath North America. The only way we can see it is indirectly through seismology. And but we have some idea of what was going on because we have the marine magnetics from the western side. So we can reconstruct what happened. So this is important input to any models to explain the Rocky Mountains. The volcanic history is another important piece of data to understand the tectonics of the western United States. So the Sierra was a volcanic arc, and at one point it finally shut down, and that's when it's thought that the subduction quit going at a normal angle and flattening out somewhat. And there's been a lot of work since the 1970s or so looking at the timing of this volcanic arc migration. And the thought is that as the plate shallows, that the volcanics would move farther inland, and then if the plate kind of drops back off, it would migrate back. And these are some other major volcanic events that some of the different models try to address. So this is just going back to one of the paleogeography figures. So here's the Sierra arc at 150 million years. It's fed by the subducting Farallon plate, and the history of where these volcanics migrated with time is part of the Rocky Mountain story. And Lang Farmer at University of Colorado, many others, have spent a lot of effort looking into this. Okay, so for the Laramide, we have shortening, compression far inland of the plate margin. So these are some Laramide basement uplifts. So these are mountain ranges that bring up really deep crustal rocks. We have the volcanic arc shutting down. We have the Colorado Plateau with some sort of less deformed lithospheric region in between. And we get crustal deformation giving us large anticlines, domes, basins, and uplifts that include deep basement rocks. So to get these mountains, there's a number of different factors. So we can have edge forces, so that's just pushing from the side. And this is from a paper that Craig Jones wrote a few years ago. And you could have basal shear traction, so that would be if the plate is kind of sliding along underneath and shearing things. You can have basal normal stresses, so that's kind of like the magic big red arrows from below that they show at national parks sometimes. And internal body forces, like gravitational potential energy, something that's high, wants to be in equilibrium with the things around it. And so some of the different hypotheses for the Laramide orogeny, most of them include some sort of flat slab subduction. So a lot of this was introduced in the 1970s, Dickinson and Snyder, Bird, and others. Maxson and Tikoff advocated terrain collision, which is just kind of a rigid indenter from the side. Livicari suggested collapse of thickened crust. And Craig Jones has an idea that involves kind of a not quite flat slab, but subhorizontal and hydrodynamic. So it includes some role of the slab interacting with the craton. So this is one of the early papers that introduced Laramide, or the flat slab idea by Dickinson and Snyder. And these are some of their cartoons showing kind of a typical subduction versus a Laramide style with kind of subhorizontal slab going far inland. And early on, they compared this to South America. So South America is a place where there's some flat slab subduction going on today. And we can see that because we can see it from the Benioff zone from where the earthquakes are as a function of depth. And in places like in the Sierra and Pampeanas in kind of Chile, Argentina, they do get some of these basement chord uplifts of mountain ranges that include deep basement rocks far inland. So this has been a pretty popular analog. Peter Bird did numerical modeling of this flat slab in the 1980s and was able to show how a flat slab could give you mountains far inland. There's been a lot of debate, though, as to whether this slab, kind of the exact geometry of the slab, he had it right along the base of the crust, which would shear away all the existing lithosphere. So there have been a lot of modifications to this since it was introduced. And this is just showing a sampling of some of the papers on the Laramide over the years. So this is from Livicari and Perry. Gene Humphreys has done a lot of nice work trying to interpret the large-scale tectonics of the western U.S. This is one of his models, Jason Salibi at Caltech. A couple more recent papers, Stegman and his group at UC San Diego think that the width of the slab plays a big role in the details of the tectonics that we have. Liu and Gurnis have done some recent numerical modeling on how some sort of buoyant ocean plateau subduction could play a big role with the Laramide. And so, actually in both of these papers, they're doing numerical modeling and also comparing it to the current seismic images. This is a paper by Craig Jones and others, mostly at University of Colorado. Brad Sageman is at Northwestern. And so their idea is that you do have some sort of subducting slab that's fairly shallow, and that this interaction with the Archean lithosphere plays an important role and gives you asthenospheric counterflow that, and actually some suction that can actually pull things down. So that came out in Geosphere. So seismic studies have helped inform some of these models and have actually at least given us some constraints on what the deep structure is, whether we could find little bits of slab remnants, what the geometry of the fault is at depth. And I'm going to start out by just showing some of the early seismic experiments that were done. That's most starting with CoCorp and what we could do before USArray, and then talk a little bit about things coming out from Earthscope, and then I'll have a fair bit of emphasis on a project that I was part of in the Bighorn Mountains in Wyoming, and that was an Earthscope flexible array deployment, which had lots of IRIS interns over the years. Michael, yeah, I should have. If I knew you were here, I would have gotten some mug shots on there, but you know they were there. Okay. Let's see. So this is from CoCorp. So CoCorp was a continental seismic reflection program that was run out of Cornell in the 1970s, and it kind of morphed into INDEP, which is a series of projects that were in Tibet and looking at the Himalaya. So what they did was they would do detailed deep crustal seismic reflection profiling across a number of places in the United States, and one of them was across the Wind Rivers, so that's in southwest Wyoming. And over the years, there had been ideas that most of the current of that thinking at that time was that these faults were kind of just vertical, going straight into the earth. And this is not the best image, but from the CoCorp, they found that these faults are more of are not going straight down into the earth. They're more at a shallow angle and can be interpreted in terms of, here's a structural geology cross-section from Eric Ersleb, who also happens to be one of the PIs on the Bighorn Project. And this is showing it's a thrust fault, or at least well modeled by a thrust fault that it is at an angle and then flattens out at depth. So that was actually a big paradigm shift in thinking about these Laramide basement uplifts, to go from this very fault vertical at depth to this kind of more shallow geometry. So that came out of CoCorp. And then in the early 90s, IRIS started the Pascal initiative, this program for array studies of the continental lithosphere. And so it was a lot like UNAVCO, which has instruments that people can borrow. IRIS Pascal has seismometers that people can borrow for their studies. And the Pascal Instrument Center is in Socorro, New Mexico. At the time of this experiment, 1992, it was at Lamont Doherty, where I was a postdoc at the time. And so I had been working on using global seismic network to look at deep structure under mostly ocean basins from different phases that bounce underneath the ocean. And just happened to be at Lamont when Pascal was getting started. So I was able to get involved with this Rocky Mountain Front experiment, which was one of the first IRIS Pascal experiments. So we drove out trucks from New York full of seismometers and deployed them all over Colorado. And then these Kansas ones were because I came along and I'm from Kansas. And actually Palco, Kansas is where Don we put a station on his farm, and he's a geophysicist who was my undergrad advisor and worked at Colorado, or at the Kansas Geological Survey. And these actually proved to be pretty important stations because to see an anomaly, you kind of need to get off of it. You can't be just on it. So these did play a pretty important role. Here's Steve Grand, who did a lot of the early work with Global Seismic Network, seeing deep structure under the Rockies. So he's involved with trying to get this higher resolution image. This is Duck Lee, who was one of Steve's grad students and did some of the first tomography of the Rocky Mountains. So that experiment was in '92, and I moved to CU in '93. And one of my first projects was actually for a long time working on the Rocky Mountain Front experiment data set. And one of the first things we did, we looked at receiver functions, which are seismic converted phases that convert at different boundaries from P to S and so forth. And we were able to get a MOHO map. And this plot is showing elevation versus MOHO depth. And if the mountains are supported by an airy crustal root, you would expect all these data dots to be in a line with thickening crust as you have higher topography. And there's quite a lot of scatter, and we find that kind of eastern Colorado into Kansas, they follow this kind of crustal thickening relation that we expect, but under some of the highest elevations, we do not see crust as thick as we expected. And this is showing gravity modeling with several different compensation mechanisms. Here's the topography going from Utah into Kansas. In the thick black is the observed gravity, and the different lines are gravity if we just have an airy root. It's shown here, so it doesn't fit the observed data very well. If we have models with Pratt isostasy, which is lateral density variations, we also have some trouble fitting unless we make it where we have both crust and mantle involved. So from this, we suggested that there must be some support of the Rocky Mountains coming from the mantle. And so we expected to see some low density in the mantle. So at the same time, Duck Lee and Steve Grand were working on some of the first seismic tomography of the Rockies. And this is just showing the Rocky Mountain Front stations. Here's Palco, Kansas, and the travel time arrivals from earthquakes at northwest back azimuth. So they had, out in Kansas, waves came in almost 5 seconds early compared to predicted, and from a standard model without lateral variation. And at Leadville and under the high mountains, they had delays of 2, almost 3 seconds. Or actually, yes, so things came in late here, came in early here. And so by looking at lots of different back azimuths and doing standard tomography, they were able to make tomographic images. So this is showing a depth slice at 150 kilometers, which they published in a JGR paper in 1996, that shows low seismic wave speeds under the Rocky Mountains, and then getting faster out into the Craton and faster under the Colorado Plateau. Ken Duker came and did a postdoc at University of Colorado and also worked with Gene Humphreys. So he was doing tomography and receiver functions with a lot of this early data. And he made this image from mosaicing together a bunch of little Pascal experiments, or moderate-sized Pascal experiments. So here's the Rocky Mountain Front. This was an experiment they ran in the Snake River Plain. There were some earlier experiments in New Mexico. And so was able to put together this image that shows this intriguing low wave speeds under the Rio Grande Rift and the Rockies. You can see the effect of Yellowstone. And also at about the same time, Suzanne Vanderlee, who was at Houston working with Gusnellet, was able to make images of a deep structure, so this 350, 450, 550, 650 kilometer depth, so looking in the mantle transition zone under the western U.S., and was able to find these different fast wave speed anomalies. So they were using global seismic network data and U.S. national network data that was available at the time. And they came up with this interpretation of interpreting those fast wave speed anomalies as different slab fragments. And then these little volcano cartoons are kind of trying to track back in time what might have been going on with, here's present day seismology, and trying to use this with tectonic history and the volcanics to get an idea of what might have been happening. Here are some models from Bunge and Grand where they combined seismology and geodynamic modeling. So this is S-wave tomography from Steve Grand, going down even deeper. So they think the subducting slab is now quite deep. This is 1,500 kilometers deep beneath the eastern U.S. And on the right are different models that Bunge came up with geodynamic modeling, trying to reproduce these. So they're kind of using these depth slices as a proxy for time slices. And then USArray came into the picture about 10 years ago, which I'm sure you're all very familiar with. So this set of 400 seismometers that's been marching across the country with spending 2 years at a time in a given area. And this is pretty close to what it looks like right now. It's very much towards the end of the lower 48. This is a picture of where USArray was this fall, and this is from this morning. So it's I think it was in Florida this fall, and it's out of there now. And these denser arrays are flexible array experiments. So we had a flexible array experiment up in Wyoming, and it happened to be at the time that USArray was there, so that was good. And the blue dots are stations that are part of the reference array that's staying in place, and then some of these purple ones are ones that have been adopted. So in Colorado, we've adopted 5 sites so that we can keep an eye on our seismicity after USArray leaves. So here's an example of some seismicity. This is from the last lower 48 USArray station in Maine, and this is 1 day of seismicity. So this is called a web recorder, and this is the URL. And so it's a whole day of seismic records, kind of mimicking what you'd see from those drums if you unwrapped it. So each line is 10 minutes, and this is midnight. Well, actually, it's GMT. So it's 0 GMT to 2400, and here's an earthquake from far away recorded on it. And the different colors don't mean anything. The colors are just to let you tell the difference between the lines. And a somewhat, I think, unexpected byproduct of USArray is that we've been able to get much better idea of seismicity in the lower 48, and that there's been a lot of what is likely to be induced seismicity, and a lot of it's in different places where there's shale gas extraction and injection of fluid. So this is a record from the station in southern Colorado near Trinidad, which is one that we adopted in large part because that's kind of where the action is in Colorado right now. That's where all the earthquakes are happening. And so this is a day of seismicity down in southern Colorado with a bunch of local earthquakes. So if I give a talk to a school group in Boulder, or Denver, usually nobody has felt an earthquake. And I gave a talk in Trinidad, and everybody has felt earthquakes. And it's really increased quite a bit since, just kind of ramped up since about 2000. So with USArray, a lot of nice tomographic images are coming out. This is an example from Scott Burdick, who was an IRIS intern long ago, and where is he now? He just finished at MIT. Okay. So he has been making images that he updates every year. So this is starting in 2007 when USArray was out in the western U.S. and red is slow, blue is fast. This is a slice at 200 kilometers depth. So it has, you can see some similarity to that early image of Ken Duker's. I think this is a little deeper slice. And then with time, this image has been refined, and they're starting to see a lot of interesting detail beneath the eastern U.S. as well. So Yellowstone, there's the Rockies. And there's a pool of instruments available for PIs to write proposals to put in more detailed experiments. So the Bighorn array is one example. So we put seismometers out in Wyoming. And there's a large pool of equipment. So this is what a broadband seismometer looks like. And this is the same kind of seismometer we used for the Rocky Mountain Front experiment. So the big change in the seismic instrumentation happened in the 80s. So we went from really big, sensitive instruments that had to be in a vault to these portable broadband instruments called force balance accelerometers in the 80s. And then the digitizers have certainly been evolving much more rapidly as disk space and electronics get smaller and cheaper. So this is what's available for USArray now. And what was available for Rocky Mountain Front experiment looked fairly similar, except something this big held maybe 150 megabytes instead of something like this holding 16 gigabytes. So we had to service the instruments more. A lot of times things were run on triggered mode, which is less than ideal. Now we can hang on to a lot more data. They have short period instruments that are available as well, and you can deploy them fairly quickly with this little box that has a solar panel on top. And then these things are what you probably have heard of. They're called Tectonics. It's a little digitizer that's it's about like the size of a coffee thermos. Takes 2 D-cell batteries, and you plug a geophone into it. So it's quite portable, and it's a RefTech 125. But the state of Texas supports some of the development, and Randy Keller was one of the folks involved. So these have been nice for active source experiments. Okay, so let's go to the Bighorns and do the flexible array experiment. So in the Bighorns, we're trying to get a better handle on what's going on with these basement-involved uplifts. CoCorp was able to give us a cross-section in one spot, and we'd like to look in another and a larger aperture. So there's still ideas kicking around. We kind of know what's going on with the faults near the surface, but down at the MOHO, these 4 different models predict 4 different things. So this one has faults cutting the MOHO. This one has thick crust under the arches. This one has thin crust under the arches. And then this one, the detachment, the MOHO geometry is not really, doesn't really play a role. It could do whatever it wants. So we set up this experiment to look in detail at the Bighorn Arch. The wind rivers are right here. And so we put out 39 broadband seismometers, and these densified USArray, which is not shown on here, but you can kind of imagine what its footprint would look like. So the red circles are the broadbands. We put out 172 intermediate period seismometers. So those are the black triangles, and those were in 5 lines. And then we had geophones that, in addition to running an active source experiment with shots, we actually left them running for 2 weeks continuously. So again, it used to be that when you put out geophones, you would just record the shots, but now we have the technology and the capacity to just keep recording the continuous wave field, so we might as well do it. And there are a lot of interesting things coming out of that. And then we had an active source experiment. And the reason this 850 is about half of 1800 is because with this, we had the instruments out, and then we just swapped them, because the batteries still only last 4 days. Here's Henry. So Henry came out, and I think it was summer 2009, and helped deploy a bunch of broadband seismometers. So this is one near Casey, Wyoming. So solar panel, digitizer, seismometers right in here. And I should also mention Freddie Bloom did a lot of the archiving for the Rocky Mountain Front experiment. So the Rocky Mountain Front experiment was done in '92, and at that point, the IRIS CMC did not require people to send in seed data, and so the data was just on exabyte tape and was event triggered and wasn't very easily available to the community. So a pretty big chore that Freddie did was to take all these exabyte tapes and make a seed archive of that data set. And 10 years after the experiment, send it to IRIS. And now that data, when people do a retrieval of a box, they get that data and they use it, whereas before that, they weren't. So that was a big contribution to the community. It's really getting used. And that was kind of at the same time you were doing the Himalayan work, right? But you ended up, you were pretty involved with it. That was right when you were learning antelope, I think. But Greg Benson was involved, which is probably what got him to switch to working with microswaller. Archiving old data is not that fun. Okay, so here's one of the short period seismometers. Here's field headquarters getting the Texans ready to deploy. And these things are still kind of dumb. You have to tell them when you're going to turn it on and off. They have to all be synced. And so doing this swapping mode required a lot of bookkeeping because you would have 2 live seismometers for the same spot at the same time. So it's live as you're driving out in the truck to put it in the field. It's live when you pick it up and you're bringing it back. So it was. So this came. The permitting. I actually hired a full-time permitter. So that was. It was a big job. It was kind of unusual for NSF to have that, but we needed it for that kind of experiment. And then just the logistics of having the broadband experiments, not too bad. We can handle that. And active source, it's just a huge logistical job. We had something like 50 people in the field and just all the vehicles and so forth. So the permitter also became logistics coordinator. And actually, Katrine Hefner helped us with when we were kind of going through that process of finding a person and figuring out what our needs were. So this is putting out one of the Texan seismometers and a box of geophones. So one of our questions is, what happened? I do not like to do time machine. Okay. One of the things we wanted to figure out is whether we could use geophone data to record earthquakes and look at the seismic structure. This is the active source experiment where we set off different explosions. And this is what that looked like. This is Steve Harder. He's at University of Texas at El Paso. We would do this at night because there's less wind noise, quieter, not as many cars driving around. These are a bunch of grad students. Can you figure out why they're laying on the ground? Yeah, they wanted to feel the vibrations better, and including the surface waves. So anyway, if these are well done, they're boring. So I guess it's still kind of exciting. You can feel it. And this is what some of the resulting seismic refraction data looks like. So this is going across 300 kilometers. Each one of these lines is one of the little Texans with a geophone. And in here, where it's black, it's just because our station spacing was smaller, so this is actually a good thing. This is where we had 500-meter station spacing. Or no, 100-meter, and out here it was 500-meter. These are surface waves here. Out here, this is probably PN, a mantle refraction. So these are direct P waves through the crust. Here's some of these phases marked. And so Lindsay Worthington, who was at Texas A&M and is now at University of New Mexico, did a lot of the work with Kate Miller on the active source experiment. So PG is direct through the P through the crust. PMP is bouncing off the moho, and PN is a mantle refraction. So with this data, she's been able to make some seismic velocity images across the Bighorn. And a rather surprising find is that we don't have thick crust. So this crustal thickness is in part is constrained by the PMP and also the PN together. And we have kind of a bowing up of the crust under the Bighorn range. With distant earthquakes, we can record those and do imaging as well. And this is work that Will Yeck has done. He's a grad student at CU. And his topography across the top. And then these different wiggles are receiver functions, which are recording seismic P to S wave conversions. And so where you have a positive bump like this, it means you're going from low velocity to higher velocity. So we interpret this as the crust mantle boundary, going from lower velocity crust to higher velocity mantle. And this also bows up under the mountains. So it's 50 going to about 40. And then these dots are just places where we've done single station measurements, which actually the red ones are the TA stations. So it can give you an idea of, with the transportable array, you would not be able to see this kind of detail. So that's 1, 2, 3, 4 of those across that area. This is a recording of a distant earthquake on all the geophones. So that's another thing we've been working on. And so this is just taking all of the geophone recordings of one earthquake and then filtering it. And you can just see a lot of energy. And we're working on different methods to extract this to get something like a kind of a seismic reflection profile of the crust and mantle from earthquake data. And this is one of our first results from that. This is a paper that Jiawei Yang wrote. And in the black are these virtual source seismograms that she constructed from the geophone recording. So the geophones are only vertical component, so you can't do the traditional receiver function analysis. But if you deconvolve out the source, you can pretend that instead your source is here and you're getting a reflection seismogram. So that's what the black wiggles are. And in color behind is the active source tomography from Lindsay Worthington, and in red is the basin thickness from industry data. And so what we can see is certainly under the Powder River Basin, this virtual source imaging gives us a very nice image of the basin. And on the west side, it actually isn't too bad. Some of this might be from out-of-plane energy or maybe just a difference in VPBS ratio. Okay, so some of the results from the Bighorn Project to date. We do not find a crustal root. We don't find faults penetrating the moho. So of those four hypotheses that we were showing early on, the lithospheric fault block and the shear thickening models don't fit our data. We reject it. The detachment model and the lithospheric buckling models are still viable hypotheses that we're exploring. The detachment surface, so that's where you have the faults kind of soling into kind of a ramp-type structure. We do not directly image that. So we're going to be doing some more work with the reflection data, the active source, to try to see if we can pull that out. But with the passive source data, there's not enough of an impedance contrast or enough anisotropy to see that. So that's still an open question. So the structural geologists really think that there has to be detachment, but we have not seen it yet. And yeah, that's the kinematic model. And then some work that I didn't show, we've done work with surface waves and shear wave splitting to look at large-scale lithospheric structure and anisotropy. And this shows that we're at the edge of a big change in lithospheric structure. So this might play something into that hydrodynamic Laramide hypothesis. And other work that we have ongoing is trying to use these passive source recordings on geophones. Well, we've gotten it to work to get basin structure, and we'd like to use it to see if that can also help inform this detachment question. And there are other groups who are starting to work on this as well. So there have been some really dramatic images coming out of an experiment in Long Beach, California, that was collected by industry, and folks at Caltech have worked with it. Some of the big questions that we're still going after are how do you get these big faults in this old lithosphere? So we have some ideas of how we get Rocky Mountains happening inboard, but where the faults tend to locate is still a bit of an open question. So pre-existing structure is always suggested as one possibility, and so knowing something also about the rheology and composition of the crustal rocks can help us get at that question. And we're also still trying to figure out what is the connection between these basement arches and the flat slab subduction. So these are some of the big picture questions still going on. I actually was at a workshop in Tucson recently where groups working on the Rockies and groups working in South America got together and were kind of comparing notes. And I'm kind of looking forward to seeing some of the new generation of geodynamic models that might be coming out informed by some of these constraints. So I'll just stop by thanking some of our helpers. There were quite a few. Are you in this one, Henry? I think this was 2010. I think, yeah. So this is from the Bighorn Project, and then going back, just loads of other folks who've helped. And let's see if I've got an Iris intern in here. There's an Iris intern. There's Mike. All right. So that's it. Thanks very much. Any questions?
Any answers? Is it fat, flat?
I can't remember right offhand, but there are several tomography models from the western U.S. in the last few years besides the MIT P one.
Mm-hmm.
There's one in Oregon,
Mm-hmm.
there's one in Berkeley, and so forth. And you didn't show those. Do they somehow agree with what you found or anything?
Yeah, so there are about 5 or 6 different models out now. And they are showing the same large-scale features, and then the details of like whether under Yellowstone, whether there's a continuous conduit or broken into pieces, or the details of the subducting slabs. I think some of those have some differences, but the large-scale structures are pretty comparable. And Gary Pavlis had a paper recently that compared a bunch of the different models, and then he has, Iris has software where you can go in and click, 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 get a cross-section, and you can pull up a bunch of the models. Yeah. So my Iris intern this summer, part of her work was doing magnetotellurics, looking at the electrical conductivity structure under the Rio Grande Rift, and then she was going onto that Iris Earthscope data viewer, I think it's called, EDV, and comparing that to different tomography cross-sections, P-wave, S-wave, from the same places. So that's a nice thing that lets you directly compare those. I think the flexible array does a lot better. So there are some different receiver function models that use just the transportable array data, and they don't see this level of detail at all. And a lot of the transportable array stations were put in sedimentary basins, in part because a lot of the mountain ranges are Forest Service land, which is tougher permitting. And the sedimentary basin, you get all sorts of reverberations. That's not the best place to put a seismometer. So some of those, it's sparser, and some of the site selection is not as good as you might get with a focused study.
So you showed a lot of images related to differences in velocities.
Mm-hmm.
In order to convert to geodynamic models, you need to be able to convert those velocity variations into density variations, and then they can be used to predict things like surface velocity variations that we have GPS control on. Do you see that as something that's going to come out of these focus studies where we can then compare what the actual surface velocities are after correcting for short-term signals?
Well, yeah, I think an integrated approach will lead to greater insight, certainly. It does seem like, to go from these images, from redite, blue light to physical properties is still a bit of an art form, and I think there's a lot of room for improvement in figuring out, what is the role of composition, of melt, of temperature, those are certainly really important problems to go after, and that's part of the reason that we're doing this magnetotelluric study, is that can also help us to get at what the physical parameters are. And something that we haven't seen much of yet is seismic attenuation studies with USArray. And attenuation is a little tougher measurement to make. You have to get the amplitudes right, or you have to look at the spectral roll-off of the phases, so the high frequencies get attenuated more. So I think having attenuation measurements, I'm kind of looking forward to seeing, instead of another suite of P and S wave models that look pretty similar, looking at attenuation or other kind of new parameters would be helpful.
So if you're advising, let's imagine you're advising IRIS as to what to do in 2018. What do you see other than going across with 10,000 stations?
2018. Well, I mean, I do like the integrated approach of not just having seismology in one compartment and geodesy in another, and electrical methods in another. I guess I like the idea of a more integrated approach going forward, or I guess, yeah, there's certainly a trade-off between a broad brush over a big area and more detailed focus areas. I think you have to be strategic. And yeah, I think that's something the community is going to have to help with, but I don't think just more stations everywhere is necessarily a good thing. I mean, long time series and a given spot is really helpful. So if you want to, find out the seismicity of a region, having 2 years is great for those 2 years, but to get the long-term seismic cycle, you're missing that. So I think there's definitely a trade-off between coarse, detailed, longer term, shorter term. So, yeah. I don't know. What would you do? Yeah. Okay. Yeah. No, and it's tough with, limited resources. But there are a lot of exciting things that have come out in terms of like tectonic tremor and flips and things that I haven't gone into at all in here that and the induced earthquakes, things that weren't really anticipated. Ambient noise tomography, actually, that's really around when the scope started, and so now having this continuous time series, there are all sorts of things we can do that are anticipated. So I think there's a lot that can be done with the existing data set. So maybe I'd say more money for analysis to university professors as opposed to facilities. How do you like that? Oh, yeah, you're going to have to extract that from the recording.
I have two questions, a short one that's focused and another one that's very broad. The focused one is, does gravity have any way of enriching or enlightening what you found in the Bighorns? Is there any reason for doing a gravity transect there area?
Yeah, so I didn't really talk much about gravity except the really early Rocky Mountain stuff. And yeah, that's certainly really important. I don't know that we need new gravity data. There's pretty decent gravity.
Okay.
And that's something, Lindsay Worthington is working on modeling that along with her active source work. And yeah, I just didn't show that.
Okay, good.
Yeah, so actually there's a Bouguer high over the Bighorn, so that's consistent with spin crust.
Yeah, right. The second question is a favorite question of mine. I love to put people onto. And what is your view of the uplift of the Colorado Plateau and the uplift of the Southern Rocky Mountains over the last 65 million years? Because, the feeling is that the current heights weren't there at the end of the Laramide orogeny. It was, everything was at sea level when it started. And so when did we get this huge regional uplift? And when did the Rockies that we see today get reinvigorated? Because they're probably not left over from 65 million years ago.
Yeah, okay. Yeah, that's a good one. Huh?
That's the hidden question. When was the Grand Canyon formed?
I think you guys need to get Becky Flowers and Carl Karlstrom and Craig Jones, I guess, in here. And just put up a little cage and let them.
Yeah, let's do that. Well, I don't.
Yeah.
I don't need the answer. I just need if you could tell us what the feelings are at the moment, the conflicting points of view, maybe. Yes.
Yeah. Well, I'm at University of Colorado, so I think I hear, Craig and Lang and Becky's opinions more than I guess Karlstrom. Yeah. But yeah, I think it's a vigorous debate. certainly on the Grand Canyon.
Oh,
And
yeah.
I'm not the real best expert to go after that.
Okay.
And the timing of the uplift of the Rockies, I mean, I liked some of the paleobotany work that was done actually in the 90s, looking at fluorescence. Some of that provided some interesting constraints on, it showed things were high here, like 30 million years ago.
Seen stuff, yeah.
Yeah, and then the geomorphologists can help inform some of this, and they can look at the current rates of incision. So it seems like there was broad uplift, and that some of the relief is actually more recent. But yeah, I don't think I think I'd have to do a little homework to give you a good
Okay, that's fine.
summary of that.
Just wondered if you had a view on it. Thank you.
You could get somebody like Craig, who has completely encyclopedic memory of all that. If you can keep up, yeah.
Okay, thank you very much, and thanks again to Ann. Appreciate it.